So welcome everybody, good afternoon, welcome back to Math 122. Today we are going to be talking over the next section, which is section 2.2. It sounds like there's a party of elephants in the room above us right now. We're also maybe going to talk a little bit about section 2.3. We might even make it all the way through if we're good. Anyways, your homework, you have a homework assignment due tomorrow night, and you have a homework assignment 2.2 is posted, but it's not due until February 22nd. That's a while away. That's not until after our first exam, which, speaking of our first exam, it's going to be on February 21st. So that is a what day? That's a Tuesday, right?
Next Tuesday.
Okay, so it's 1 week from today, because today is Valentine's Day. So that's when your exam is going to be. On Thursday this week, we will not have a quiz. Instead, we will spend the entire 75 minutes reviewing. So what I'd like you all to do is to come to class that day with questions about topics and questions about specific homework questions. Because remember, your exam problems are going to be drawn directly from the pool of homework assignments. And the homework assignments which will be relevant for the exam will be 1.1 to 1.9 as well as 2.1. So all of the exam questions, just like the quiz questions, will be drawn word for word from those homework assignments. Yes, Braden?
Around how many questions is it?
I usually do about 3 pages, 9 questions, something around there is usually how it is. I might do, oh, okay, wait, this is a 75-minute class. It'll probably be 4 pages. So probably I'll do, round about a question from every section, maybe 2 if it's an important thing. But yeah, ask me again on Thursday. I'll have a better idea of how long it'll be. Yeah.
If they're straight from the homework, do we get a calculator on the test?
No, you don't get a calculator on the test. And so if I give you a question that involves like some kind of like interest business or whatever, it'll be like a make the formula, or it'll be like solve for this thing in general terms. And you can leave your answer in terms of natural logs, or you can leave your answer in terms of an improper fraction or whatever, okay? So I'll make the math work out nicely. You won't have to do anything crazy, but multiplying up to 12 times 12, that sort of thing. Nothing crazy. Any other questions? Okay, so where was I? Oh yes, that was the exam. So we review on Thursday, so it would be great if between now and then you took a look at the homework assignments, 1.1 to 1.9 and 2.1, and you picked out some of the problems which you felt like were pretty hard for you when you were trying to do them. And then we can do those in class on Thursday, or I can give you, or if you say, Tom, can you just monologue about exponential functions, then I can monologue about exponential functions, or whatever you may want to work on. And if nobody has anything to say, which I'm hoping that isn't the case, but if nobody has anything to say, then I will just pick some things at random for us to work on. Okay? So that's the review. Regarding office hours, I want to remind everyone, on Tuesday, my office hours, I'm just in the Math Tutoring Center from 10 to 12. Okay, so I'm not in my office from 12 to 1 on Tuesdays. On Thursdays, I'm in my office from 11:30 to 1. And sorry, did I say Tuesdays again? I meant to say Thursdays. On Thursdays, I'm in my office from 11:30 to 1, and on Wednesdays, I'm in my office from 3 to 4. If you can't go to office hours, you can go to the Math Tutoring Center from 10 to 4 Monday through Thursday, or 10 to 2 on a Friday, or you can go to the SI sessions with our SI Jacob at these times and days and places. And you can also go to any of the other SI sessions. If you prefer to go to a different SI because of location or time or what have you, then you can do that as well. You don't need to go to the SI session for our class specifically. Speaking of those 3 resources, Office Hours, Math Tutoring Center, and SI, I'm offering an extra credit opportunity for the exam. And it will work in the following way. If you go to my office hours or the Math Tutoring Center or the SI session of any SI, including ours, Jacob, then if you go for 1 hour, I will give you plus 2% on your exam score as long as you turn in a written note from whatever instructor you go to. Okay, if you go to me, you don't need a written note. But if you go to Jacob, or if you go to the Math Tutoring Center, or you go to another SI, then have them write you a note that looks like this, that says, okay, John Doe attended my SI session for at least 1 hour, and then their name and their signature and who they are, okay, in terms of what are they, like, are they an SI, grad student, instructor, whatever. If you if you get that note and turn it in to me, then I'll give you plus 2% on your exam score, okay, for your coming up exam. Sound good? All right, cool. Any questions about the extra credit? Yep.
I just wanted to make an announcement. In addition to the SI sessions this week, there'll be an exam review on Sunday. I don't know what time yet, but that'll be just like an extra SI session if you have any last minute questions before the examination.
Okay, so special SI exam review session on Sunday. For how long?
It'll be 2 hours, I think.
Okay, 2 hours on Sunday, time TBD, but look out for the email, okay? Because Jacob will send an email, and maybe we'll talk more about that on Thursday. Okay? Any other questions, comments, or concerns for the good of the order? Okay, it doesn't seem like there are any, so let's talk about math. And let's start by talking about what we talked about last time. So last time we introduced this notion of a derivative. So holy crap, we're actually doing calculus now. Nobody panic. I'm not panicking. So you shouldn't panic. No one should panic, okay? So what is the derivative? It's just the instantaneous rate of change, okay? So before, okay, we learned about how to find the slope of lines like this, and we called the slope of lines like this to be the average rate of change over this interval from like t1 to t2. And we noticed, well, it kind of describes, loosely speaking, the slope of the function in between. But what if I want to know like the actual slope of the function at a point? Which another way to think about that is to say, what is the slope of the tangent line? Okay, so we spent some time last time deriving a methodology for doing this, which looked like the following. And I want to focus in strongly on the picture of what's happening here. We take the average rate of change over smaller and smaller intervals, and you can see that the slopes of the corresponding lines become closer and closer to the slope of the tangent line, which is ultimately what we want to know, is the slope of the tangent line. So we just take the slope of these secant lines, where the secant line is becoming closer and closer to the tangent line, and then that helps us to look at the pattern and make an educated guess about what we think the actual slope of the tangent line is. Okay, so we did an example of that last time. We came up with a methodology and everything. Okay, and then what did we talk about? Okay, some more terminology and notation. Okay, so when I write this symbol, okay, f with a little apostrophe like that, the way we read it out loud is f prime of a, okay, or f prime of x or whatever, or f prime of 2. Okay, and what it represents is the instantaneous rate of change of f of x at x equals a. Okay, or you could say that in the same way by saying slope of f at t equals a, or slope of f at a, or you can write this f prime of a notation, or you could say it's the slope of the tangent line to f of x at x equals a. That's another way of saying it. Okay, so just a bunch of verbiage, so to speak, okay, to talk about derivatives and rates of change. So the next thing we learned about was, well, when is the slope going to be, when is the derivative going to be positive, negative, or 0? Ultimately, what that came down to is, well, it's a question about the slope at a given point. Are we increasing or are we decreasing? If we're going up, the slope is positive and the derivative is therefore positive. If we're going down, then the slope of the tangent line is negative, and so therefore the derivative, which is the slope of the tangent line, is negative, okay? And one thing that you may have seen on your homework is, okay, just because you have a function which is negative, doesn't mean that the derivative's negative. Because if we took a look at this red function here, and we asked ourselves, let's call it g, and we asked ourselves, what is g prime of negative 2? We would actually say that it is a positive number. Even though the function is beneath the x-axis, we're thinking like, isn't it negative? But the derivative isn't about the height of the function. The derivative is about the slope of the function, okay? Which is to say, look, if I take a look at this line here, which is the tangent line, its slope is a positive number. So therefore, the derivative is positive, okay? And that's what we learned last time. So any questions about what we talked about last time? Okay, then I'm going to go over one quick example which I didn't get to last time because I've seen that it has come up on your homework assignment, which is you have like some kind of table and you are supposed to estimate the instantaneous velocity or the instantaneous rate of change of a function based on a table, okay? Based on a table. All right, so the first question is, why is it impossible to exactly determine the instantaneous velocity of this grapefruit? Okay, so we're throwing a grapefruit into the air, it's going up, and then probably it's coming back down, right? So why can we not tell how fast it's going at time t equals to 1 from this table? Well, we have limited information. We basically are told how tall the grapefruit is off of the ground at sort of inconsistent intervals, right? They tell us how far it is at 0, 1, 2, 3, 4, 5, 6, and that's it. Okay, so what does it do? It starts at 6, and then it goes up to 90, 142, 162. So, okay, here's 90, here's 142, 162, and then what does it do? It starts dropping back down, 150, 106, and then 30. Okay, so it looks something like this, and we might imagine that the function looks like this, right? But what are we asking? What we are asking for is the instantaneous velocity, which is to say, if we knew what this curve was, what would be the slope of the tangent line at this point? And it's a big question mark because we don't actually have the function. Okay, we don't actually have the function. We just have a handful of data points, a handful of points on this curve. We don't know what the curve itself is actually doing. You know, who knows? You could connect these points by like a picture which looks like this, right? Although it wouldn't make much sense given what we know about gravity, right? But the point is, we don't actually know what this curve looks like. So we can't actually determine what the slope of the tangent line is. However, what you might imagine is the following. You might guess that the picture looks something like this. Yeah? Based on what you know about grapefruits being thrown into the air. And if you wanted to know what is the slope of this line, well, you don't know what the slope of that line is, but you can easily compute the slope of two other lines. You can compute the slope of this line, and you can compute the slope of, geez, I'm running out of colors. How about green? You could also compute the slope of this line. Yes? And you could say, well, this line has a slightly different slope than this line, but probably they're both fairly similar to this one. And you know what we might actually expect is that this one in the middle is probably somewhere in between the slope of these two lines. Okay? Is somewhere in between the slope of these lines. So if we wanted to estimate the instantaneous velocity, I would say a good way of doing that would be to say that the instantaneous velocity is probably approximately equal to the average velocity before plus the average velocity after divided by 2. Okay, I'm going to take an average. So if I do that, I can just see that, well, from 0 to 1, the average velocity was 90 minus 6 over 1 minus 0. And then the average velocity from 1 to 2 was 142 minus 90 over 2 minus 1. We divide all of that by 2. So 90 minus 6, that's 84. And then we've got plus 142 minus 90 is 52. Add these two things together. We get 136. Is that right? Over 2. Which would be 68, I think. Are we happy with that, or did I make a numerical mistake there? Okay, seems like we're happy. So the point is, look, you look at the average velocity between 0 and 1, you look at the average velocity between 1 and 2, presumably the actual velocity at 1 is somewhere in between those. So a good guess would be to say, well, maybe we're halfway in between those, which is exactly what an average of two numbers is. It's the number which is halfway between them, right? The average of 50 and 100 is 75, right? It's the number which is halfway between 50 and 100. Okay, so this is how you do the one on your homework regarding this. Was that you who was asking about that, Drew? Does that make sense?
Yeah, I got it.
Okay. And Karan? Okay, good. All right, any questions on that one before we move on to 2.2? All right, I'm going to talk some more, and then we're going to have some group work. So just to remind you, I know I keep saying this, and I sound like a broken record, but what is the terminology? We say instantaneous rate of change, which sometimes I write it IROC, okay? That's what I mean when I say that. As opposed to AROC, what do you think that one stands for? Yeah, average rate of change. Okay, so that's what I call it, and it represents the slope of f at A, or the slope of the tangent line to f at A, and the way we write it sometimes is using this prime notation, f prime of A. Okay, so we're going to do a quick example here where we're going to make some guesstimations, okay? We're going to make some guesstimations on, or just estimations. Why not? Let's just do estimations. Okay, so at -2, -1, 0, 1, 2, 3, 4, 5, we're going to try to figure out what is f prime of x. Okay, so how do we do that? Well, we're going to try to make an okay picture of the tangent line. I would say this one probably looks something like that. That looks pretty good to me for the tangent line at -2. And it looks like I'm going up from what? From -2 to -1. So my run was 1. My rise was how many? 5. So my rise was 5. My run was 1. So I'd call that 5. Okay, about 5. Then how about at -1? Okay, we're going to get real colorful here. At -1, this is the point, and the tangent line looks something like this probably. No, what am I doing? Tangent line maybe looks like that. Okay, it's not the best tangent line I ever drew. But it looks like I go up about, what, 1.5 as I go over 1, so maybe like 1.5. And then at 0, what is it? At 0, now it looks kind of like that. Which maybe I need to extend it so I can see. What is this? What I like to do when I have lines which I can't exactly tell what their slope is I like to look for the points where they actually go through the corners. Because then I know I'm going to get nice even numbers, right? Or not even numbers, but nice whole numbers. So if I do from here to here, the run is 4 and the rise is -3. So I would call this -3/4. Okay. Then 1. Geez, this is getting tedious. Okay, what is it at 1? Well, God damn it. Okay, well, it looks like we went, how much did we go over? We went over 1 and we went down. how much did we go down? We went down about this much, which is probably, it's pretty close to 2, I feel like. Pretty close to 2. In fact, if we just pick this thing up and move it over, I bet it's, oh god. Okay, if we just pick this thing up and move it over, it's probably about 2. Yeah, it's pretty close to 2. Okay, so we'll call that -2. It doesn't have to be perfect. It's just a guess. Okay, so let's keep going at 2. Now we're down here. Let's say it still looks like -2 to me. And at 3, maybe something like that. Looks like about -1. And then at 4, maybe like so. No. Something like that. I don't know, maybe that's just regular old 1. And then at 5, it's something larger than that. I don't know, maybe we're back up to 3 or something like that. Okay, you get the point, right? So what do? I'm just drawing some lines which look like lines of tangency, and I'm trying to guess their slope by looking at like the grid marks, right? I'm just trying to guess how many grid marks did I go over versus how much did I go up, right? Rise over run, that's how I figure out the slope of a line. Okay, and let's notice something. Well, as we go from left to right, let's read the numbers out. 5, -1.5, -3/4, -2. And then -2, and then -1, 1, 3. So it's like going down, 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 and then it's turning around, and then it's going up, up, and then up some more, okay? So what could we do? Well, we could plot all of these points here, right? This is a table of values with inputs being x values and outputs being these guys here. So in fact, okay, we could call this a function of x, okay? We could call this a function of x. And we could even draw its graph. So let's do that. Let's draw its graph. Why don't I just draw its graph on here? What does it look like? Well, we start at 5 and then -1.5. So we start at 5. Okay, then we got to go down to -1.5. And then we got to go down to 1.5. And then we got to go down to -3/4. And then we got to go down to -2, right? And then we're again at -2. And then we go up to -1. And then up to 1. And then up to 3. Okay. Holy crap. So, what are we noticing? We're noticing that the derivative of a function can be used to define a new function. Okay? A new function, which looks different. Okay? It looks different. In particular, there's times where the actual function's positive, but the derivative is negative, right? And there's times where the function's going up that the derivative's going down, and so on and so forth. We get a whole new different function, but this function is a new function which says something about the original one. Okay, it says something about the original one, and that's going to be what we are basically studying for the next 2 chapters after this one. Okay? All right. So let me draw that on, maybe with a looks something like this, yeah? Okay, so that was fun. Any questions about this this first problem here? Okay, then I'm going to give you a quick definition, I guess, of the derivative function, what it is, okay? It accepts, like any other function, an input, x, and returns, right? It's going to take an input and it's going to give you an output. And what is that output is what I want to now describe. The output is the slope of the parent function, f of x. So we sometimes call it the parent function. At the given x value. Okay, at the given x value. So it accepts an input x and it returns to you the slope of a different function at that x value. Okay? So let me show you what I mean on the previous graph. In this case, okay, f prime of -1 is equal to 1.5. That tells us that, look, this is a function in and of itself. If the input is -1, how do I figure out what the output is? What I'm supposed to do is I take that -1, I go to where x is -1, and I go take a look at the function. And I ask myself, what is the slope of the function at this point? That is the slope of this tangent line here. And that's what the output will be, is the slope of this tangent line. And I can use that to make the new function f prime, whose height, okay, this height here, which we said is 1.5, is 1.5 because the slope of this tangent line is 1.5. Okay? So the height of the derivative function is given by the slope of another function. Okay, its parent function. Okay, we call it the parent function because the derivative comes from the original function. Okay. All right, questions about that so far before we do a little... Oh, well, we got one more thing and then some group work. All right, so the next thing that I want to talk about is just when is a function going to be increasing and what that means for the derivative, okay? So we've kind of already seen the three scenarios, right? Let me draw them for you. Scenario 1, the function, as we move from left to right, is increasing. Yes? Oh my God, I hate it when that happens. Okay. So the function is increasing. So f prime of 0, or sorry, f prime in this region is going to be positive. Okay? In other words, the slope, okay, the slope is going to be what? What goes here? Slope of f is positive. All right, let me color coordinate this. Next up. No, next up. We have something like this. So on this region, the function is decreasing, right? It's going down. If I was walking on this thing, I'd be going downhill, right? That means my height is decreasing. Yes? So what does that mean? Well, that means that the derivative is going to be negative because the derivative just tells us what is the slope of the tangent line. And that tells us that f is going to be decreasing. Okay, and then finally, the third intermediate option. Why don't I draw a whole new picture? So this is my function. Looks like that. So this is f of x. Then, at this point, what does the tangent line look like here? It's just a horizontal line. Okay, the tangent line is just a horizontal line. So we would say that f is constant when the slope is 0. And the slope is the derivative, right? The derivative is the slope is the derivative, right? So f prime is actually equal to 0 when we have a constant function. Okay, we're not even supposed to learn that until later on, but I'm giving you that one for free. All right, any questions on that one? So this tells us function is increasing when the derivative is positive. Function is decreasing, derivative is negative. Okay? I feel like it's extra warm in here today. All right, let's do some group work. So we're going to work on problem number 3, and it's a hard problem number 3, okay? But I want you to do your very best, and I'm going to come around and help you if you get stuck, okay? So problem 3, we got a similar type of picture here, okay? And we want to answer 3 questions. First of all, for which values of x is the derivative equal to 0, okay? And then for which values of x is g increasing or decreasing, right? And you're going to notice that there's too many to count, right? How many points at which the function has a positive slope? You can't count them. There's infinitely many of them, but we have a way of describing infinite collections of numbers. Does anybody remember how we describe infinite collections of numbers? A range, which can be expressed in terms of... Yeah, you're on the right track. What do you call that? When we put like one number, and then another number. What do we call these guys?
Set.
A set. But this one in particular is a special kind of set, which has another name on top of that. But it is a set.
Intervals.
There we go. Intervals. Okay, so we're going to need to use intervals for part B. All right, then part C, self-explanatory. So go ahead and get started. I'll be walking around.
Oh, so just like where it turns. Oh.
Yeah.
Right.
That was pretty good. You got the same answer.
So where it's
Excellent. Trickier, right?
that prime or cheaper is 0.
Okay, so we're doing increasing here. So let me ask you, what's happening to the left of 1.5? Are we increasing or decreasing?
It's increasing.
Okay. Remember, it's kind of tricky because when you look at this thing initially, we think like, oh, it's below the x-axis, so it's negative, right? But the derivative isn't about whether we're below the x-axis, is it? It's about whether we're going up or going down. So at this point, right, here, we're still going up for this section, right? So we should probably go all the way to -2. You see what I mean? Or negative 10. Yeah, exactly. But what we're describing is really the x value. We're describing this set of x values. You got it? And then it tells us we're going up from here. Did you catch that, Seth?
Kind of like drunkenly said yes to the date was planned today, and she actually went on that.
Like Sherry went on it.
Like she's on it right now. I'm dying. She had no idea she was going to go until like yesterday.
That sounds
Based on the
Derivative is positive.
I forgot.
We're just basically
Derivative is negative. If a number goes from being
Let's drop that.
positive to being negative, you know what it has to do first?
Because it's increasing.
You don't get on game clock part. I'm not on a date there.
Exactly. That's why I think I need that times two.
Here's 0.
Like where else can you feel the same romance?
If my number goes from being positive to
Dynamics.
and then at some later
Worst
time,
part, it wasn't
it goes
a date, it
down,
was
down,
just
down, 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 and then
went
later
with
it's
me.
negative. What does it have to do first?
Oh, I see. It was totally on
Like,
the other side.
Has to go
morning
through
of the
0,
last
right? So if
minute
it's
students day,
positive
and it was
here,
like 8 o'clock in the
negative
morning,
here,
and so my clothes was like,
what do you think happens?
like, it was so
Probably has 0, and why is that? Because let's draw a tangent at this point.
That's the premier spot to take it down.
If you flat horizontal,
Either
right?
that or like
And the derivative tells us
Panera.
slope of that, which is 0.
That's what my boys said last year, because like, you know,
So where's the
It's zero.
I was so
What a
sad.
talent, dude.
I was so sad. I was like, okay.
What a ladies man. Why, dude? No.
3? Yeah, on the top, right? But then what about the other one? Yeah, at the very bottom, right? Which happens
Especially
when
since
x
they both do
is
Cardi
4.
B and Offset meal.
I will try.
I do too. I saw like, because I thought it was
So,
fake up until like the day
Yeah,
it
no,
was.
it's
How about where it's increasing?
I was like, there's no way that's real. And then McDonald's tweeted about it. I was like, there's no. It's probably something
There's
nasty.
a lot of fish.
It's probably something nasty. Cardi B, because she always be eating weird
Not
food
crazy.
combos.
Because remember,
Like
when we're talking
was
about
at McDonald's,
increasing and decreasing, we're describing the x value for which we're increasing or decreasing. So I think we're describing the like from left to right. Okay, as we go from left to right, where is the point on the left and right axis at which we stop?
And for offset, a quarter
Increasing.
pounder.
It's x goes from negative infinity up to x equals
Plus a large order of
0.
fries and
Okay.
a apple pie.
All the way up to 0. So we need to describe all the numbers between negative infinity and 0, which we do
It's,
using.
you know, it's not as weird as Cardi B's
Does that help?
that she had at McDonald's. It was always weird because it was always like you can find.
There's no quiz. Well, first of all, we don't have class tomorrow. Oh, burrito, oh, yeah.
It's not as weird as I thought it was gonna be.
The section is
I'm
it's
not
quiz
taking
4,
it
right?
girl to
Section
McDonald's.
1.6.
Let's get this Cardi B offset meal.
Are they even like together still? I mean, clearly, but I did not think they were.
I don't know. I wouldn't call it together. I'd call it like,
Are each other's baby?
yeah, they're co-parenting while fucking other people. I'd say, or at least Offset is.
I love offset.
I think, dude, it's so funny.
That's
There's that
okay.
one clip of like when Cardi B was in the room and Varsity heard like 3 fucking phones, so she couldn't find her
Not
phone.
yet. Okay, so
I don't know.
here's what we want to think about.
It's just like not a good relationship.
She's increasing on these two.
But hey, they got a McDonald's meal with each other, and I don't have a McDonald's meal.
That makes them so
Graphs,
You know,
are positive, which means negative
I
infinity.
feel like I get out of bounds for a Times Day McDonald's meal. Just be called like
Well, the first
so
one
nice on food.
is actually negative between
Talk about like next Thursday,
like
like
negative
80 or
Yeah, next
80.
Thursday is gonna be like 82. This Thursday it's
So it should be
negative infinity up to
Yeah, I could live with it just being like
So
how it is.
one fails
for a
then.
little minute.
How about three?
Today is three also failed. Today's down.
So we're stuck with two. Four using positive on the left side, and negative in the middle.
Well, that's what I'm saying, I mean, it makes sense, but.
Alright, how about y'all over here? Good?
How about you?
I'm pretty good. I meant specifically with respect to the math, but yes. Okay, these all look great. Okay. Yeah.
So I must see. We know which one it is. So it's supposed to be increasing from negative to zero.
Yeah, so here's the thing. F is increasing means that the derivative is positive. F is decreasing means the derivative is negative. So what are we looking for? We're looking for a function which is positive from negative infinity up to zero and from 4 to
Now you
infinity.
see,
That's this
I
one.
like to think
Positive
that I'm a
here.
professional
Positive
hater.
here.
So like,
And then
I wake up at
between 0 and 4
5:45
it
every
is.
morning just to hate.
Wait, so,
no, I'm on my grind.
so zero, okay.
I go to the
So
gym now
just
to work out.
positive, negative, like, going positive.
Well, right when we're talking about the graph of the
Yeah, see, this had my, he needs Valentine's Day.
Oh my god, I saw someone arrested. Yeah. I love it.
He needs Valentine's Day. Yeah, I'm a professional hater, so I wouldn't say that I love Valentine's Day, but I do love hating on Valentine's Day.
I'm a sucker for like
Yes.
I get so excited. I was
Let me
like,
know
so
if the
excited.
explanation is not inadequate.
More than Christmas. Are
Okay, let's come back together as a group. I saw great work out there. So, what are we noticing about when g prime of x is equal to 0? Is that telling us anything about this graph? What does it tell us about the original function when the derivative is 0? Anyone noticing a pattern there? Yeah?
It's the change in direction.
Yeah, it's where our function changes in direction. I love the way that you put that. It's where it changes in direction. In other words, it goes from being increasing to being decreasing, or it goes from being decreasing to being increasing. There's two places that happens, at a maximum and a minimum. Why might I be interested in that from a business perspective? Why do I care about the maximum or the minimum of a function?
I don't know, it kind of helps you gauge where you are currently. You know what like your previous maximum and minimum are. You can kind of gauge things off of that.
Yeah, definitely. Or it might help you to, I as a business person might want to maximize certain aspects of my business, minimize other aspects of my business, right? For example, I might want to maximize my profits, right? Or I might want to minimize my carbon emissions, right? So being able to identify where is the minimum or maximum on a function, or where is the minimum going to be at some future time, right, is super useful from a business perspective. And we just learned that, look, maximums and minimums occur when the derivative is equal to 0, which is at x equals 0 and x equals to 4, right? You can see that the tangent line is going to be horizontal at both of these points. Okay? All right, so that's part 1. And part 2 is a little bit tricky, okay? A little bit tricky. We got to use interval notation. Well, we can see that our function's increasing from here up to about here, and then it starts decreasing. But what we want to describe here is the collection of x values associated with this part of the graph, okay? The x values associated with this part of the graph can be seen here. These are all the x values, which are associated with the increasing part of the graph. So I'm looking to describe all of the x values which go up to 0. So one way you could do that, I would accept two answers here. Either negative infinity up to 0, or if you want, negative 2 up to 0. Okay, one of those. But we'll stick with negative infinity. Then, so that's increasing on, and this interval, and I'm going to do a union because I'm going to conjoin two sets. And the other set on which I'm increasing is the set of x values associated with this part of the graph, which can be seen here. And those x values are neatly expressed by the interval 4, comma, infinity. Or if you want, you could go like 4, comma, I don't know, 5.5 or something like that if you wanted to be nitpicky about it. Not nitpicky, if you want to be specific about it. Okay, and where are we decreasing? We're decreasing in between. So that's from 0 to 4. Now I have a question, which I'm hoping someone will answer for me. I said I'm increasing from here up to here, but I didn't include 0. And I'm decreasing from here to here, but I didn't include 0. Why didn't I include 0 in the sets on which I'm increasing or decreasing?
Because it's constant.
I would be very careful about that language, but you're on the right track. Alex, do you have something to add?
Yeah. Is it? Are we supposed to use brackets?
Well, technically we are not supposed to use brackets. Okay, technically we are not supposed to use brackets, and here is why. I can only say that I am increasing at a point in terms of where I just came from and where I am going to thereafter. If I look at the point up here, if I approach from a leftwards direction, I'm increasing. But if I leave the point from a rightwards direction, I'm decreasing. So in order to say that I'm increasing, okay, or in order to say that I'm decreasing, what I need to say is that, look, on some small region surrounding the point, I am going up over that whole region, okay, or I'm going down over that whole region. It's not true for this point because I'm increasing to the left, but I'm decreasing to the right. So you might say, well, is it true that we are constant at that point? And again, it's not quite the same. So we told a tiny bit of a white lie when we said, look, f prime of equals 0 is equal to f is constant. Not exactly, not exactly. This is why I drew this separate picture for the constant guy, right? Because what do we need? We need to be constant on some small interval about the point, okay? Some small interval about this point. In order to say that we are constant at the point, we have to be constant nearby, okay? And how nearby? There just needs to be an amount of distance, okay, in each direction on which we are increasing. So it could be like 0.0000001 or something like that, something tiny on each side, okay? But we need a little bit of actually flat part, okay? Because even though this function evens out, the function itself is never actually flat. Does that make sense? So it's never actually flat for a period of time. Okay, it's never flat for a period of time. So we wouldn't use the terminology that we're constant at this point. But based on my definition, which I just gave you, I can see why you would say that. So it's just a little bit of a nitpicky thing, but we're definitely not increasing at that point, and we're definitely not decreasing at that point. So it just turns out that that's not a trichotomy of situations, okay? You can be neither increasing nor decreasing nor constant at a point, and that's what's happening at maximum and minimum here. Okay, further questions about, we need to finish still, right? Okay, well, based on our observations in part A to B, we want to make the graph of the derivative. Well, if the function g is increasing or decreasing on these intervals, then this tells us that on these intervals, g prime is what? If g itself is increasing, what does that tell me about the derivative?
It's positive.
Good, it's positive. And if it's decreasing, that tells me that g is negative. G prime is negative, excuse me. So I'm looking for a graph which for the x values from negative infinity up to 0 and from 4 to infinity, the graph is positive. Is that true for this picture? No, because I have this section which is negative and I have this section which is negative. So it's definitely not this one. So we can eliminate this one. And we can eliminate the third one for a similar reason. From negative 2 up to 0, okay, the function should be positive. But what is it? Here it is negative, okay? So this is like the opposite of what we want. So that's not true. But this one is positive from negative 2 to 0 and from 4 to infinity. Yeah, we're always above here. And from 0 to 4, the function should be negative, right? Should be negative. Okay? All right. So that's how we figure out what the picture should be. Are there any questions on this example? Is this helping you to get a better feel for the derivative? And what the derivative is, what it says about a function, and how to graph it? We feeling okay? Let's have some thumbs. How are we feeling about the material so far? Way up in the sky. Thumbs up if we're good. Thumbs down if we're confused. Okay. That's looking like mostly fairly okay. All right. If you have more confusion about this, then make sure that you see me in office hours or MTC or SI or something like that. Okay, so you stay on top of it. All right, we're going to move on then. Two. How much time I got? Oh, plenty of time. This is beautiful. I've never felt like I had so much time in my life. All right, so let's talk about Liveness notation. We're going to skip to section 2.3. Okay, so this is nothing new. It's just a different way of writing what we already know. Okay, it's just a different way of writing what we already know. Okay, so way back in the day when calculus was invented, the story goes actually that it was invented simultaneously by two different individuals. Those individuals were Isaac Newton. Okay, Isaac Newton, who, by the way, was insane. And second of all, God, what is his name? Wolfgang Leonhard Leibniz, or something like that. Something like that. Wolfgang something Leibniz. Anyways, they invented calculus at the same time, and so there's two different notations which kind of spread from their geographic location until it became a point where, like, some people were using one notation, some people were using the other, and the result is today we just kind of use both interchangeably, okay? So what does Liveness notation actually look like? Well, what he wanted to say was, instead of using this sort of average rate of change business, he described f of b minus f of a over b minus a as rise over run. Okay, and the notation he used for that was delta y, so capital delta y over capital delta x, where delta literally means change in, okay? So change in y coordinates, okay, that's y2 minus y1, right? Change in x coordinates, that's x2 minus x1. So he said, look, the way I can approximate the derivative, which is the slope of this blue line, is to say, well, it's kind of close to the slope of this secant line, which is given by delta y over delta x. That's this rise over this run, okay? Then what did he do? He did the same process as Newton. He says, we're going to take this green dot and we're going to steadily move it closer to the other dot. And we're going to successively check the slope of lines which are more and more similar to the actual line that we care about, okay? So what did we do? We replaced the delta, okay, which represents a change in, with this d. And what does d represent? In this case, d represents an infinitesimal, infinitesimal change in. Okay, which is to say, look, this notation means the number which you would get if you took delta y over delta x, but you made the interval over which you're studying this quantity smaller and smaller and smaller and smaller and smaller to the point of insanity. Okay? So that's dy dx. We use little d as in like lowercase delta, as in like small version of the capital D. Okay? Small version of capital D. As for why we don't use the actual lowercase delta, you're going to have to ask someone else about that. Okay, so in terms of notation, okay, if we have a function y equals f of x, then we describe the derivative function, okay, in the following three ways. You can say d dx of y, which is the same thing as dy dx, dy over dx, which is the same thing as f prime of x. Okay, so these three things make the same thing, and I mean the same thing, and I just want to say something briefly about this notation, okay, which you can think of this kind of as y, the function, being plugged in to the derivative operator. Okay, operator, that's a big word. What does operator mean? It means like do the derivative of. Okay, so d dx, parentheses, is called the derivative operator. Derivative operator. So it literally means do the derivative of whatever's inside of these parentheses, okay? Which you can write as the derivative of y or as f prime of x. Okay? All right, so one more thing about Leibniz notation is, okay, how do we plug in numbers? We can plug in numbers to f prime of x really easily. We just put a 2 where the x was. For dy dx, what we do is we write dy dx, and then we do a little bar. And at the bottom of the bar, we put the number which we're going to plug in, okay, which is x equals 2. Okay, so the way this reads is dy dx evaluated at x equals 2. Dy dx evaluated at x equals 2. Any questions about Leibniz notation so far? Okay, so sometimes, going forward, sometimes questions will be phrased in terms of Leibniz notation. Sometimes questions will be phrased in terms of Newton's notation. You can use whatever notation you like, okay? So if you want to stick with the notation of the problem, that's sort of customary. But if you would prefer to just translate into Newton's language, that's fine too. Okay, use whatever notation you feel happiest with. But you need to know how to read Leibniz notation, and at least. Okay. So while we're at it, why don't we talk about the units of a derivative function really quickly? Can I scroll away? Okay, I'm scrolling away now. The units of a derivative function are the units of y divided by the units of x. Okay, surprise. The units of x. For example, if d of t is miles and t is in hours, then I could make a graph of d of t. And let's say my trip looks something like, this would be kind of realistic, right? Because what does it say? I move slowly initially, and then I'm going faster and faster away from home, and then I slow down, and I stop, right? So if I look at this point here, and I said, oh, what is the slope of this line? And if I said the slope of this line is 30, okay, then I would say d prime of, and let's say that happens at 1 hour, I would say d prime of 1 is 30, and the units are, of course, miles per hour, because the rate of change okay, the rate of change of the distance function is the velocity. So it kind of makes sense that it's going to be measured in miles per hour. But what are the units? The units of d, distance is measured in miles, and time is measured in hours. So you divide those two, you get miles per hour. All right, so that's how we get the units. So later on, we'll see business applications that could be like dollars per unit. Okay, dollars per unit, or something like that. Or it could be, I don't know, something else. All right, any questions on the units? Do we feel okay about that? Okay, I think it helps if you look at it in, if you look at it in Liveness notation, it kind of makes perfect sense. You have a change in y, your output, over a change in x, your input. Of course, the units are going to be whatever are the units of the numerator divided by whatever the units of the denominator are, right? Okay. All right, let's move on to something else. Okay, so I'm going to do a quick example. Ooh, yeah. I'm going to do a quick example. All right, so I want you all to work through this one with me as I go, okay? All right, so Sam's puppy, Meatball, which is kind of a weird name for a dog, but okay. It makes me think of freaking Aqua Teen Hunger Force, if you've ever seen that show. Anyways, Meatball has weight function W, okay, equals g of t. All right, so the weight function is a function of time. So the input is time, in other words, the age, and the output is the weight of the puppy. Okay, so the output is the weight of the puppy. So, question. If we have a puppy, do we expect g prime of t to be positive or negative? I want to ask somebody raise their hand and tell me positive or negative and why you think so. Yeah, Stephanie. Positive because, yeah, it's positive because it's a puppy. Puppies grow. So the weight of the puppy is an increasing function. And increasing functions have positive derivative. Okay, so I would say g prime of t is greater than 0 because g of t, the weight function, is an increasing function. Right? The puppy is growing, it's gaining weight. Okay, sweet. That wasn't too bad. I'm going to scroll now to do another page. Is that okay? All right, here we go. All right, write the derivative. So remember, w equals g of t. So the derivative, okay, we could write it as g prime of t. How would I write it using Liveness notation? Close, but what's the output of this function? The input is time, and the output is weight, w. So we want to do change in w, because g is just the function which takes us from t to w. So change in w is what we're looking for, which would be dy, sorry, not dy, dw over dt in this case, okay, dw dt. So these two things are interchangeable notation-wise. Okay, now let's do some interpretation. We haven't done that in a while. Interpret the equation g prime of 8 is equal to 6. Well, that says that the slope of g of t at t equals 8, which t equals 8 means what? T equals 8 means, remember, t is Meatball's age in months. So t is equal to 8 means that the puppy Meatball is 8 months old. Right? Is what? 6. And what are my units going to be? Well, the units are going to be the units of the top divided by the units of the bottom. So what's the units of the top? Weight is measured in, what is it? Is it pounds? Pounds. So the numerator should be pounds, and the denominator should be months. Okay? All right, so 6 pounds per month. So what does that mean? It says when the puppy is 8 months old, it is growing. Not only is it growing, we know how fast it is growing. at a rate of 6 pounds per month. Okay, that's how we could make that into a sentence. Any questions on that one? Because this interpretation stuff is pretty important. It's going to come back kind of like over and over again on the homework and exams and quizzes and stuff like that. So I really want to focus on this one. How do we feel about that? Is there anything that could be a little bit clearer or that you'd like me to explain one more time? I really don't mind. Okay, then let's do the last part, which says what? Assuming that Meatball is healthy, what value do you expect G prime of 36 to take and why? Let's start with what is G prime of 36? G prime of 36, what does that represent? Without getting into what is the actual value of this. Whatever that number is going to describe something about this problem, right? G prime of 36 would give us a number which describes what in terms of the problem? Can someone answer that for me? What does it describe? G prime of 36. So the months are 36. Good. And how about G prime? What does G prime tell us about the puppy? The growth rate, yes. So the rate at which this dog is gaining weight after 36 months, okay, represents growth rate after 36 months. What do you think? In terms of the value, what do we expect it might take? Who's got a dog? Whose dog is older than 3 years old? Are they growing? No, and they're probably not losing weight, assuming that the dog is healthy, right? So we would expect G prime of 36, or I would expect G prime of 36 is probably 0, since 3-year-old dogs are fully grown, typically. Okay? 3-year-old dogs are fully grown, so they're not growing anymore. So from month to month, the weight is probably steady, right? Or constant would be another way of saying that. Okay, last topic I'm going to discuss for today. Well, okay, any questions on that? We happy with our study of Meatball the dog? Okay, then one more thing that I'm going to talk about. And I'm just going to talk about it in a very simple way today, and we'll talk about it in more detail next time, okay? But here's how I want to talk about it. So, what does this say? Tangent line approximation. What I want to describe to you is just what it is, okay? Just what it is. And then after the exam, we'll talk about how to do it in more detail. So, if x minus a is small, whoa, okay. Let's first of all say that a is given. A is a given number. And let's say that the distance between x and a, which is given by the absolute value of x minus a, okay, this is the distance between x and a, is small. We're not going to quantify that yet. And let t of x be a new function, which is given by the equation of the tangent line, okay, the equation of the tangent line, to f of x at that point x equals a. Okay, so let's make a quick picture here of what the hell is going on. Let's say this is f of x. And a is given, so let's just pick a spot for a. Here's a. Then what? We can make the tangent line. I don't like that tangent line. That's better. Okay, so this is the tangent line. So this is t of x. Okay, so what is it saying? It says, look, if x minus a is small, meaning that the x value is fairly close to a, okay, fairly close to a. Still got 5 minutes. Let's wait to pack up. I promise I'm going to be quick here. All right, so if we're close to a, then what is true? F of x, the height of the function, is close to t of x, the height of the tangent line. Okay? So what does it say? It says, look, if you pick an x value, which is pretty close to a, like this one, then what is true? This height here is f of x. And this, let me go to dashed. This height here, which goes all the way up to here, is t of x. And you can see that basically in this general region, the height of the tangent line is basically the same, okay, is basically the same as the height of the function, which is to say you can use it to approximate the function. So let's say, for example, I don't know anything about what the function is doing after this. Okay, this is very common in business applications. You have data of what's happening up to now, and you want to know what's going to happen in the future, like tomorrow. So let's say I know how much money I made the last 10 days in a row, and I want to know how much money I'm going to make on the 11th day. Well, I know, going from left to right, I know how much money I made today, and I know how fast my money has been increasing generally over the last 10 days, which can tell me a guess of how much money I'm going to make on the 11th day, okay? Which is to say that, look, if you know generally where is your current height and what is your current trajectory, well, assuming that things don't change drastically, your height on the next day or the next second or whatever is probably going to be similar to if you were to just start at that point and go in the same direction, okay? So the one final comment I want to make on this is, look, this x minus a is small is really, really important, right? Let me show you why. If this function goes on and on forever like this, and this function goes like this, then later on the difference between the heights could be enormous, okay? The difference in heights could be enormous later on, okay? So it only works when you are close to a. Any questions about that? Yeah, Alex?
But like with like A, and then like which is like the point above it, like I'm trying to do the whole like x thing is and then like end with the fx. Like,
It's okay. So let me go through really quickly. A is a number.
yeah.
A is a number which is given to you. T and f of x are functions which are known. Your goal is to guess what is the value of f when you plug in a number which is close to a. What this says is that the output will be similar to the output of if you just plug that into this function instead, which is desirable because this function you know how to plug into very easily. Okay, but we'll talk about this more next time. We can chat after class if you want a better description. All right, let's close there for today. Thanks for your attention.